Okay, so good day, students. My name is WANDILE Mabanga, and this is our second block, first lecture, and it's going to be vectors and scalars. And the prescribed textbook, which is on your screen, is Introduction to Physics by John D. Cartnell and Kenneth W. Wilson. I've got the 9th edition here, but even if you have an earlier edition, I think that would also do. And then we'll also use a study guide. The study guide for 2015 is a red book. So the learner guide is compiled by Mrs. D. Duplessis for 2015. And in particular, we are looking at learning unit number 8. So learning unit number 8 is on page, let's just have a look. Okay, so we're looking at pages 36, 37, 38, up to 39. Okay, so what is the plan? So the plan for these lectures is we'll look at sections 1.5 up to sections 1.9 from the book, and section 1.5 is just introducing, so we're introducing scalars and vectors, and then 1.6 we'll look at vector addition and subtraction. Then we'll move on to the more important, which I've called here the Holy Grail, which is vector components, and that's going to be very useful even when we look at Newton's laws. And then we'll also look at vector addition using components, so that uses the previous section. And finally we'll look at some questions which are from the study guide. Okay, so as I've said, the material that we'll be using, it's the physics textbook, which is Introduction to Physics by Cartnell and Johnson, and then the study guide is by Darlene Duplessis, the 2015 edition. Okay, so let's start. So we will start with section 1.5. Okay, so we'll start with scalars and vectors. Okay, to start, I would like to distinguish between what we call a number, what we call a scalar, and what we call a vector. Okay, so a number is a mathematical object, and it's something which we use to count, so we use this to count. So for example, we can say 5. And we might be counting rands, so it would be something like 5 rands. But the rand is not important. We are interested in the 5. Okay, and then a scalar is a number plus an extra thing which we call a unit. And a unit is just similar to a name. So it's a number with a name. And this is no longer a mathematical object, it's now a physical quantity. So it's a physical quantity. Okay, and then finally, let's look at what is a vector. And a vector is a number plus a unit plus, so I'm going to use the space over here, plus direction. Okay, so what are the examples? An example for a number is we might have 2 oranges, so we'll just say 2. And for a scalar, it might be the length of a ruler, which is just 30 centimeters. So the 30 part is the number part. The centimeter is the name, which is the unit. So it tells you that you are talking about length in this example. Okay, so it's just the name of the thing you're talking about. And then for a vector, we use an arrow. So we would draw an arrow instead of a number line, as in the case of a scalar. So that arrow is, it has properties. So this part is called the head, and this part is called the tail. The length of the arrow is called the magnitude, and that's the number plus the unit part. Okay, and then the direction at which this arrow is pointed, that's the direction of the vector. Okay, so just to show you a nice summary of what I'm talking about. So if we check what we have now is, we said a number is a mathematical object and it's used to count. An example would be 5. So for example, we can say we have 1, 2, 3, 4, 5 apples. Okay, so I just counted them out, and that's the number of apples. That's just a mathematical object. But then since we're studying physics, we are interested in physical quantities. So an example of a physical quantity is a scalar, and that's the most basic. It's used, instead of counting now, we measure a physical quantity. So we use this to measure a physical quantity, and an example would be 13 kilometers. Okay, so just a reminder again, a scalar is a number plus a unit, and a unit tells us what we are measuring. Okay, so there are 3 basic units that we have. It's a unit for mass, which is measured in kilograms. So that's the SI unit. It's a standard international system that we use. So we measure mass in kilograms. And the SI units are basically related to our own experience as human beings. So my weight, if you ask me what is my mass, I would say something like 70 kilograms. I wouldn't say 70,000 grams. It's a big number, and that's not sensible. So we use kilograms, and then we've got distance, so how long someone walks or how long something is, and the unit for that is meters. And then finally we measure time. We'd say we'll meet in another 30 minutes, but the SI unit is seconds. And finally, for vectors, we need a number, a unit, and a direction. So an example would be, I'm walking 27 kilometers, so I'm driving 27 kilometers east. And we said there are different representations. So for example, here we drew some circles and counted them, and we said we have 5 apples. Over here, if we want to add, so here when you add, say for example, apples, your friend has, or James has 2 apples, Kagiso has 7 apples, and they want to know how many they have in total. Then you just count them. So you'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's the total number of apples they have. Whereas for scalars, we use the same thing. So if you started off and you walked 50 meters, met a friend, and then walked with your friend to school for another 55 meters, then the total distance that you walked from A to C is actually the distance from A to B plus the distance from B to C. So we just add the numbers 50 and 55. The unit is just there just to tell us what we are talking about. So the total in that case would be 105 meters. Okay, and then now the key is how do we then add vectors, and we have one rule. So we needed to promote this notion to add direction as well, and the rule is we add vectors head to tail. Okay, so we start off, so if say for example you have 2 vectors, vector 1, and you want to add vector 2, let me just show you here on the screen. So we have vector 1 and we want to add vector 2. For vectors, there's a notation we use, and we draw half an arrow on top of what we are talking about to show that it's very different from a scalar and the fact that it has direction. So if I want to add these 2 vectors, there are 2 ways I can add them. So I can either start and draw vector 1. So there's my vector 1, and then draw vector 2. So if I now draw vector 2, that's how vector 2 looks like. So then that's my result, and my result is I started over here and I stopped over there. Okay, so if this is the beginning and that's the end, then what was my total displacement or result? So the result is from the start to the stop, and we call that vector r. So vector r was a result of walking 1 and then 2. Okay, notice this is not the only way, so there's another way. So I can start with 2 instead. So if I start with 2, that's how I would walk, and then 1, and then we see that the result is the same. So the result is from the start to where we stopped, which is the end point, and that is my r. So in this case you can say that I started with 2 and I finished with 1, so r is still 2 plus 1, and the order in which I add is not important, so this is the same as 1 plus 2. Okay, so that is what I have over here. I've just drawn just one way. So you start off and you draw vector 1. At the head of vector 1, you start with the tail of vector 2, and you draw vector 2 exactly as it is. Then where it stops, that's where you stopped. So your starting point was over here and your end point is over there. So the result of this trip was from here to there. Okay, so that's a resultant. And now the question that we would like to answer. So we've just completed section 1.5, which is scalars and vectors. Now we want to know, how do we actually add vectors? And the way we add vectors is quite simple. I think let's start with the simplest examples. So the simplest example is if you walk in a straight line. So here we are looking at vector addition. Okay, so it's the same thing this side, vector addition. So say I start at point A to point B, and then from point B I walk a further distance to point C. Okay, so my starting point was at A, and my finish point or my end point was or is at C. So if we now call this vector 1 from A to B, then from B to C call that vector 2, we can see that the sum of those two, which we called the resultant, is from A to C, and we just draw a line directed from the starting point to the end point, and that's our result. So you can see easily that R is equals to A plus, so not A plus B, R equals 1 plus 2. Okay, so but then how do we subtract vectors? So you might be interested in what is the difference of vectors. So if we work with this equation, we can immediately see that R, so if I take 1 to the other side, minus 1, the sign changes to a minus, so R minus 1 equals 2, or equivalently R minus 2. So if I now take 2 to the other side and leave 1, then I get R minus 2 is the vector 1. Okay, I'm interested in this case because it's simpler. So then what do we learn from our vectors? Remember that our vector R was from point A all the way to point C, and it was directed towards C. So I start off and I draw vector R, and that's my R. Then now I must minus vector 2, and recall that 2 was this vector over here. It started at B and it went to C, so if I can just redraw B, there's our B. Now when I'm minusing 2, that means I'm walking in the opposite direction. So instead of going from B to C, I'm gonna go from C to B. Okay, so now minus B is a vector starting from C all the way back to B. So that vector is minus 2. So minus 2, not minus B. So let's correct that. That vector over there is minus 2. So then we learn that if we add R and minus 2, what do we have? From our diagram, our starting point now is at A, because we started at A and we moved to C. Then from C we moved back to B. So our end point is at B. And the result was we moved from A to B. And that's just the vector one which we've drawn before. So we learned that R plus minus 2, which is the same as R minus 2, equals 1. So vector subtraction is just vector addition, where you reverse the vectors that you are subtracting. Okay, so you add the reverse of those vectors. So in this case, we added to vector R the reverse of vector 2. Okay, so in summary, if we check over here, just again, if we start point A and then we move to point B with the vector A in black, and we start again from B to C with the black vector B, then the result was we started over here, we end at C, and it's just the red line which is directed from A to C, and we write the vector addition in that way. So it's just the vector R equals vector A plus vector B. Okay, note however that we can rewrite this and take the B to the other side. In that case we get R minus B, which is equal to the vector A. How do we get vector A? We start off, we draw vector R, and vector R was the vector from A to C. And then now, remember that B was from B to C. So now we reverse the direction of B, and it starts from C to B. That's minus B. So we add to R minus B, which is the same as subtracting B. And the result was we started at A and we end at B, which is our vector A. So that's R minus B equals to A. Okay, so that's how we add vectors. Just a reminder that the rule for vector addition is vectors add from head to tail, and the result is the vector drawn from the starting point to the end point, and we call this vector a resultant vector. Okay, so let's look at another example where we've got three vectors, A, B, and C. A is at an angle theta with respect to the x-axis, B is at an angle alpha with respect to the y-axis, and C is at some angle gamma with respect to the x-axis. We want to know what is the result of these three vectors. So the result of those three vectors, if we now check, we start by drawing one of the vectors. So in this case I'm going to start with vector A. So there's our vector A. It forms an angle theta with respect to the positive x-axis, and then after drawing A, I'm going to draw vector B. So vector B was a vector over here, pointed that way, and it formed an angle alpha with respect to the negative y-axis, so that's our vector B. So notice I'm starting from the head of vector A, and that's where I have my tail for vector B, and then I just draw my arrow as I've drawn here. Then finally we need vector C. So the final vector starts at the head of where we stopped from B, and if I now draw C, in this case it goes back to where we started. Okay, and remember that C formed an angle alpha with respect to the x-axis. So this closed triangle over here is a special case, and this is what is called equilibrium. And what is equilibrium? So equilibrium is when you have the sum of your vectors equal to 0. So that means the resultant of those vectors equal to 0. And this is mainly used in Newton's laws, where the forces balance each other. Okay, so that's what we get. So if we check here, I've already drawn out what we get. So what you will see is I've drawn my vector A over there, and it's at an angle theta with respect to the x-axis. Then after that, from the head of A, I draw vector B, which is like this. So B is exactly like that, and the angle it formed with the y-axis was alpha. So there's my alpha with respect to the negative y-axis. And finally, from B, I need to draw a vector C, which forms an angle gamma with respect to the x-axis. And there's my C, and it forms an angle gamma with respect to the x-axis. And our result in this case, we started over here, we end there, so the resultant is just no motion. So that's equivalent to 0. Okay, and I just said we call this equilibrium, which means the resultant vector equals to 0. Okay, so now let's look at another example. So another example is where we have say some vector A, and A is drawn in that direction. So it forms an angle of theta with respect to the positive x-axis. And then if we now have another vector B, which forms an angle alpha with respect to the y-axis, what is the resultant of these two vectors? We have two ways of finding the resultant, and we get the same answer. Either we start off and we draw vector A, or we start off and draw vector B. So I've drawn both cases over here. So the first one, I started off and I drew vector A, which forms an angle theta with respect to the x-axis. And then from the head of vector A, I start and I draw my vector B, which is pointed that way. And if it forms an angle alpha with respect to the y-axis, that means it forms an angle 90 minus alpha with respect to the x-axis, because the x and the y form are orthogonal. So the angle between the x and the y-axis is 90 degrees. So using that fact, the other angle over here will be 90 minus alpha. So that's what I've drawn here. So that's my 90 minus alpha, and my endpoint is over there. How do we find the resultant? The resultant is from the starting point to the end point, and it's an arrow from the start to the end. So that's how our result looks like. Notice it forms some angle with respect to the negative x-axis, which I've called beta here. Okay, or alternatively, we can start with vector B. So if this is my starting point, I draw B. It forms an angle 90 minus alpha with respect to the x-axis, and then draw vector A from where I stopped for B, and it forms an angle theta with respect to the x-axis, and my endpoint is over there. So then we get the resultant from there to there, and it's the same resultant as this one. It's just that my diagram here is not drawn to scale, but you can see that the direction is the same, and the angle, we said the angle that it forms with respect to the x-axis is just beta. Okay, and how do we then write down the result? So the result R is given by the R. So the R without the arrow tells us the magnitude, that is the scalar part. So it's the number plus the unit that will give us the R, and that's just the length of this line. And so for example, you'd measure it using a ruler, and the angle which you measure using a compass when you're using this method of graphical solutions is beta. So you just take out your compass and measure this angle over here, and the degrees that you get in this case would be beta degrees, which is north of west. So starting from west, I'm going north and I'm going beta degrees up. Okay, and then if now we're interested in instead of a plus b, we want to know what is a minus b. Remember that now I have to draw b, but instead of having b pointed that way, I reverse the direction of b. So b is now pointed that way. So if I can just show you over here what I mean. So then remember that we had A forming an angle theta with respect to the x-axis, so that's our y, that's our x, and then we had the vector B at an angle alpha with respect to the y, and we said the other angle, which is the smaller one, is just 90 degrees minus alpha. So then what is A and minus B? A minus B, I draw the same thing. So there's my A. So that's A. And the angle that it forms is theta. And then now I need to draw B. So remember that B was directed like that. So now minus B is the opposite of B. So I reverse, I draw along the same line, the same vector. So minus B, if this was B, that's our minus B. It's in the opposite direction. Okay, same magnitude but opposite direction. So the angle it forms over here is our same angle as this one. So that's 90 minus alpha. So now if I add those two, first I have vector A. So I've got vector A, which forms an angle theta with respect to the x-axis. And then now I have to draw vector B. So vector B is something like that, and actually not B, minus B. So the angle it forms is 90 minus alpha with respect to the x-axis. So that's our minus B. And you can see that to get the result, that's our starting point, and that's our end point. So the resultant is from the starting point to the end point. In this case, it's from here to there. So that vector over there is our A plus minus B. Okay, so which is just A minus B. Okay, so if we can just check my solution over here. So that's the same thing which I've been talking about. So we've got A over there, it forms an angle theta with respect to the x-axis, and then we have minus B, which is in the opposite direction as B, same magnitude. So you reverse the direction of B, and the angle it forms with respect to the x-axis is 90 minus alpha, and that's the resultant is from the starting point to the end point, and that's just A plus negative B, and it's then arrow like that. Notice that this is very different from the resultant we got before. Okay, so that completes the section which is 1.6. So we've just completed vector addition and vector subtraction. So now we are going to talk about vector components. And this is very important. So this is the key of what we will talk about. So for vector components, has an x and a y component. So you can draw any vector and I will show you the x and the y components. Okay, and this simplifies our calculations when we add vectors. So what we've just done with vector addition, we added vectors using diagrams, and we said, how do you get the resultant? You measure the length of the line, and to get the direction, you measure the angle. And I mean, that can be quite inaccurate depending on your drawing skills. So we want an answer which is absolutely accurate and it has nothing to do with your drawing skills. So we are now going to talk about components, and that will help us to calculate more accurately. So the first important thing is every vector has an x and a y component. Okay, and we draw a Cartesian plane. This is called a Cartesian plane because of the inventor. So that's your x direction and it's perpendicular to your y direction, which is called the y-axis. And on these two directions we can then draw some vectors. So an example is I can have a vector which only has an x direction. So say we have some vector a. So the fact that every vector has an x and a y component means for any vector a, not particularly the one that I've drawn over here, any vector a is given by the sum of two vectors, which is the x component plus the y component. And this is true in general. So let's just make sure that we box this equation, and this equation is true all the time. Okay, so in particular in our case over here, for our a equals ax plus ay. Sorry, so let's just erase that. That's a typo. So plus ay. But in this case, a only has an x component, there is no y component, so the y component here is 0, so then a is just ax, it's just the x component. Okay, we can also draw another vector, let's call it vector b, which only has a y component, so it's directed in the y component. So b in the y direction, so b is equals to bx plus by, and these are vectors, but in this case we've just said that there is no x contribution, so b is just by. Okay, but a general vector has both x and y, so an example is what I've just drawn, and the x component is the vector over there directed in the x direction. So you draw a vector from the starting point and you end where it meets the y-axis. So you draw a vector from the starting point up to where your y-axis corresponds to the end point. That's your x contribution. So if we call this vector r, rx is from the starting point to where our vector meets the y-axis from the end point, and then where we ended off, we start our y component and we draw it all the way to the end point. So you draw a vector directed all the way to the end point. So that's your y component. And these two are perpendicular, and then the vector r forms an angle theta with respect to the x-axis. Okay, so in general r equals rx plus ry. Don't forget that these are vectors. So just to summarize what we've just said, let's just make sure this is fine. Okay, so every vector has an x and a y component, and we use a Cartesian plane to draw our vectors and find the components. So the horizontal belongs to x and the vertical is what we associate with the y. And if now I draw an example, so I drew an example of a horizontal vector a, and since it's horizontal it only has an x component because there's no y component. Okay, and then similarly I can draw another vector which only has a vertical direction, and the y component gives the whole contribution because there's no x contribution. And we said in general r is just the sum of the x contribution and the y contribution. So we draw the x first, so we start from the starting point and draw a vector that starts here and it ends where the y-axis meets the endpoint. So draw the y-axis from the endpoint all the way down or all the way up, and then draw your vector from the starting point to there. The horizontal vector would be your x contribution, and your y contribution is from where you stopped from the x all the way to the endpoint. Okay, so that's vector components. And then let's have a look at some conventions. So we've got conventions, and the conventions are if you go up, if your vector is directed up, it has a positive y component. If your vector is directed down, it has a negative y component. If a vector is directed to the right, it has a positive x component. If it's directed to the left, it has a negative x component. Okay, so for example, there are actually four. You can see that there are four vectors that I can draw here. So let's just see what I'm talking about. So if we check now, that was our y and that's our x. So we said if you draw a vector that goes up, that's positive for y. If it goes down, that's negative for y. If it goes to the right, that's positive for x. If it goes to the left, that's negative for the x. So there are four different vectors that I can draw, and I can draw a vector which is a plus for both x and y. So x is pointed that way and y is pointed up, so it's plus plus. Or I can have a vector which is pointed in the second quadrant, in the fourth quadrant, and you can see that my x is positive, my y is negative. And I can also have a vector in the third quadrant where my y is negative and my x is negative. And finally I can have a vector which has positive y and negative y. Okay, so those are all the four different vectors that you can have, and I've just summarized that over here. So for example, if my vector is directed in that direction, you can see that my x has a positive component, my y has a positive component. So how do we write down the vector? Remember that we wrote down the magnitude. So in this case, the magnitude of this vector is just the ry, and that's the number plus the unit, and then the direction is given by the positive. So the fact that this has a positive y component, we just write a plus in front of it, and that plus is the direction. Okay. Similarly, we have plus rx for the x component for this vector, and the other three cases are where you have plus ry for the y, but you have minus rx for the x component. So the minus tells us that we have a negative x component which is towards the negative x-axis. So that's the sign, which is the direction, and then the magnitude is just the vector without the arrow. So it's just the symbol without the arrow. So that's how we get rx over here. And of course we can have a case where both x and y components are negative, and finally where the x component is negative but the y component is positive. Okay, so now what is the question we would like to answer is, what is the x component in terms of the vector r, and what is the y component in terms of the vector r and theta. So most of the time, if you have a vector, they'll give you the angle that it forms, either with respect to the x-axis or the y-axis, and they'll give you the magnitude of the vector that they've drawn, and you need to find the x component and the y component using trigonometry. So what do we have? We have the following. So if now I have a vector r and they give me an angle theta with respect to the x-axis, so in this case it's the positive x-axis, the x component from trigonometry is, so x, which is in this case adjacent, so adjacent over hypotenuse, just to remind you, was cos theta. So rx over r is cos theta. Let's just write it down over here.